AI is a powerful tool.
This summit can help ensure that artificial intelligence charts a course that benefits humanity and bolsters our shared values.
Welcome to AI for Good, the leading action-oriented, global and inclusive United Nations platform on AI. Organized by ITU, in partnership with 40 UN sister organizations, and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished panelists and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Hello everyone, thank you for joining us today and welcome to this AI for Good session on Towards Fusion Energy with the help of AI. Many thanks to our speaker, Dr. Michael Churchill, a fusion energy scientist in the Computational Sciences Department at Princeton's Plasma Physics Laboratory. I'm Jaharge for the International Atomic Energy Agency. The IAEA is the World Center for Cooperation in the nuclear field and seeks to promote the peaceful use and application of nuclear technology. This AI for Good session will give an overview of how AI can contribute to advancing fusion energy through enhancing simulation. Please type your questions and comments into the neural network chat function. We'll try to go through those during the session. For those of you working or interested in fusion and plasma science, make sure you check out the IAEA's AI for Fusion platform. I will share the link in the chat. Our coordinated research project on artificial intelligence for accelerating fusion R&D is developing AI applications in fusion science at an international level. Please consider attending our next workshop on AI for accelerating fusion and plasma science from the 28th of November until the 1st of December in Vienna, Austria. Link in the chat as well. Without further ado, please welcome Dr. Michael Churchill.
All right, thanks so much. Let me pull up my screen here. Okay, everything's okay. So thanks to everyone for coming out. It's a great pleasure to be able to talk a little about fusion energy and specifically ways that we're pursuing using artificial intelligence and machine learning to enhance simulation and really help us to our ultimate goal of providing a clean and an abundant energy source for the world. So I'm Michael Churchill. Like was said, I'm at the Princeton Plasma Physics Lab, and I wanted to thank all of my colleagues here who have contributed at various points to all of this research material. So for those that have been looking around, there's been a lot of interest in using machine learning to accelerate simulation. And this has been growing tremendously over the past years with the advent of deep learning and applying this specifically to numerical solvers and mesh-based simulations. Examples on the right from DeepMind, for example, down on the left, using neural operators for improving underground carbon storage, machine learning for particle accelerator systems, speeding up simulations that are used there. I could go on with many examples, and there's a lot of room to use machine learning to help accelerate simulations and traditional numerical solvers. But there's also, as we'll see, a lot of caution that needs to be applied in how it's used in order to get accurate results. You may have also seen a lot of headlines in the news lately about fusion energy. So fusion energy has had a long history of research for the past 70 or so years, and recently has seen a kind of resurgence in interest, especially from private companies being funded by people to pursue nuclear fusion and make it a reality. With that has come some breakthroughs recently, for example, from Lawrence Livermore, achieving break even with the National Ignition Facility. ITER, which is a large magnetic confinement fusion device, is being built in the south of France. And there are tens of fusion startups that are all pursuing various concepts to try to make fusion energy a reality. So obviously these two areas, of course, can be tied together. So how do we apply effectively machine learning to help us further advance the goals of fusion energy? So I'm going to be talking specifically today about our research. I focus on magnetic confinement fusion. So I have here a nice video that was put together of the ITER tokamak. And this kind of shows the complexity of the devices that are created. And for those that may not know, as a basic overview, this is a tokamak device, which is basically a donut, which you fill with a hot plasma, and you heat up this plasma until you achieve the high temperatures required to achieve fusion energy. So these are very complicated devices in terms of the physics involved, the plasma physics on the inside, but also it's a very coupled problem between physics and engineering, because as you can see, there are many devices and components that go into the design and operation of these devices. And so fusion as a field has often turned to simulation to help better understand the complex plasma physics that occur inside the plasma, and also help design the machines so that they can perform in a way that will get us to a break-even condition. So I'm putting here a couple different diagnostics that are typically on these fusion devices, just to show somewhat of the breadth of different modalities that are present on fusion devices. There are usually hundreds of different types of instruments being used to measure various parts of the plasma. And that's because it's very difficult sometimes to measure all of the different components of the plasma that could be useful for both controlling and understanding how the plasma is behaving. And this can be even more complicated because of the right graph that you see, which shows the broad range of time and spatial scales which physics phenomena occur in plasma physics, in fusion tokamak plasmas. So this, is scaling something like 14 orders of magnitude. And so to cover these various different physics areas, we have many simulators that have been created to try to show us what is happening inside of the plasma when we don't have the coverage with the diagnostics. So I'm going to be talking today about a couple different simulators and how we can apply machine learning to help us accelerate the process of using these simulations to better understand and plan for future fusion energy devices. So I'm first going to talk about accelerating fusion energy simulations. So this is maybe more towards the beginning topics of accelerating traditional simulations. And I'll show you a large scale turbulence code where we take out a piece of it and accelerate that kernel, which is the Fokker-Planck collision operator. And then I'm going to show you some work that we've been pursuing, tying together fusion energy simulation and experimental data comparison. And this is because often there is so much data generated by experiments, and simulations can't quite cover it all necessarily. You have a good opportunity to leverage machine learning to help make fast surrogates, which can be used to do statistical inference and extract physical parameters from the experimental data, which are consistent with the simulations. Okay, so first part. So I work with in a large group that's at PPPL and various other institutions using a code called XGC. This is a large scale, what's called gyrokinetic code. So it's 3-dimensional in space, 2-dimensional in velocity, and full F. So it simulates the entire particle distribution function. And it's what's called a particle and cell code, which I'll show a little more on the next slide. It's focused on simulating the turbulence and transport, especially in the tokamak edge. And this is a critical piece of information that's needed because it is needed to predict the heat loads to the wall, ensure that you don't melt your wall, and also ensure that you are able to have a high-performing edge region, which will lead to higher core performance and ultimately the fusion energy output that you want. Because of its full F nature and the very tricky time scales and spatial scales that are needed to be resolved, this XGC code is massively parallel, and it has to run typically on extremely large supercomputers such as Summit and the exascale computers, Frontier and coming Aurora. So while there's various pieces that go into the XGC code, there's one particular one that's important for the edge, and that's the collisions between particles. And XGC uses what's called the Fokker-Planck collision operator, and a fully nonlinear one, solved using Picard iteration. One of the difficulties with this, though, is that this naturally scales quadratically with the number of species. So if you have different types of ions that are involved, such as impurities that come into the plasma, and you need to simulate those to get a better understanding of how the edge will behave, then this collision operator will be expensive. So simulating devices such as ITER, which is the large tokamak being built in France, with tungsten, will require multiple charge state impurities and potentially make the collision operator the bottleneck for these XGC simulations. So accelerating the collision operator will allow for more detailed simulations, including many impurities. Just briefly, the basic algorithm is taking what's called the Boltzmann equation. This is very basic. On the left-hand side, it shows you can derive some equations of motion, which in this code is gyrokinetic, which tells you how particles will move and accelerate. And XGC uses this particle and cell method, which basically samples a bunch of particles and moves them according to these equations of motion on the left-hand side, and then deposits all of those particles onto spatial grids in also 2D velocity space. And then in that 2D velocity space, this right-hand side of the equation, which represents the collisions and other sources such as heating and neutrals, etc. And those are solved for on this 2D Eulerian grid. And so there's particles moving all around, and then there's a very fine mesh that at each point in the spatial mesh, there's a 2D velocity grid. And the collisions are separable such that each spatial point is independent, and you can run the collision operator on each 2D grid. So this is the equation. I won't go through all of the details of it, but suffice it to say that there are also physics constraints associated with the Fokker-Planck collision operator. These collisions should conserve particles. You shouldn't annihilate particles in these fusion plasmas, momentum and energy. So there's exchange of momentum and energy between colliding species, but there should be no creation or destruction. So as I mentioned, XGC histograms the particles and then creates these 2D distribution functions, one at each spatial point X, and it's spatially independent. So each configuration space point is processed independently. So this is kind of the basic setup that you pass in your distribution functions from different species, here ions and electrons, and out of your Fokker-Planck iterative solver comes the change in the distribution function that should be applied. And you can see an example of one of these distribution functions. And it's important to note that this is a particle in cell code, so there actually is noise inherent to this process, similar to Monte Carlo methods. And so this will come up a little later in how we think about in trained neural networks. Okay, and so the traditional solver that we have currently in XGC uses is implicit, uses backward Euler and Picard iteration for fixed point iteration, and has a convergence criteria of the change in the density, momentum, and energy should be below some threshold. And the validation tests that have been run agree on simple analytical expressions, agree with what the analytical relaxation of the temperatures of these distribution functions would be. So you can see here two colliding species of ions and electrons, and they both have different energy in the different parallel and perpendicular directions. And so you can see that the electrons, as the collision operator is applied, the electrons start to come together and isotropize or get the same parallel and perpendicular temperature. The ions do the same, but on a longer time scale. And then eventually both of those species come together and are equilibrated together. Okay, let me skip that. All right, so thinking about what we could do with machine learning, my first thought a number of years ago was, well, this is very similar to a lot of the computer vision work that was being done at the time in machine learning, looking at semantic and instance segmentation. So if you haven't seen this, basically you can take an image here, X, with some height and width of your image and color channels, red, green, blue in that case, pass it through a neural network that has been trained, and out you come with a per pixel estimate of what the class should be, here represented in N. So here we've taken an image and it can segment the image. So each pixel here represents, this is identified as a person, this is identified as a car, etc. And normally encoder-decoder type architectures are used for segmentation. So you kind of, you can see this encoding step and then decoding step as it's typically represented. And the intuition is that data lies on a lower dimensional manifold. And so this type of architecture should aid in identifying the kind of lower level semantic structure. Okay, so our original work, we essentially took a encoder-decoder neural network that was used for image segmentation and applied that to our particular case. So we gathered a large set of XGC data and trained the model such that it was going for the targeted change in the distribution function that we expected from the traditional solver. And importantly, we looked closely at, well, how should we apply the loss to compare? So an obvious one is applying L2 loss. It's different than the class prediction that you often see in instance segmentation. Here, it's we really care about the real values of this delta Fi. And so there's an L2 loss applied between these two images. for a per pixel prediction. And then we have this conservation loss that we added in, which is trying to enforce at some level that these conservation quantities, the density, momentum, and energy change should be as low as possible. And this is what we call fixed penalty, because often you have this prefactor, which is used in the loss constraint, and that is often typically fixed, or you can play some games to adjust it manually. But at some level, you can keep this fixed and train the neural network. So the architecture that we turned to was something called reseg. This is actually a fairly old architecture back in 2015 from the Toronto group. It uses as an encoder VGG16 and then a couple RNN-based decoders for upsampling. It's about 2.6 million parameters. The reason we started with this actually was this was trained on CFAR10, and the size of the data that we had was almost exactly this, 32 by 31 for our case. And so by just a simple padding to 32 by 32, we were able to apply this and get out the delta Fi. So intuition-wise, one of the nice things about this reseg also with the RNNs on the decoder side is it helps you on the encoder side, you can get kind of the local features, and the RNN side can help aid in covering the global features. So you can see our initial results with this. It performed pretty well. We were getting down to losses of 10 to the -4 in the ion, momentum, and energy. We wanted to go even further, though. So we did some work with what's called an algorithm that was created by Alp Denner and Argonne at the time, called Stochastic Augmented Lagrangian for training. If you remember the fixed penalty lambdas that we had, those impose a very specific result, and can be a little bit difficult to train with, because at the very beginning of your training, your neural network may not understand very well what the solution should be, and so your conservation quantities can be fairly large, and that will have an effect downstream. So, so this particular method was an intelligent way to effectively modify those lambda parameters, so that as your constraints became smaller and smaller, your lambda parameters would increase, such that you would have more importance on the constraints versus the L2 loss. And in this way, you could effectively ensure that as the conservation quantity decreased as you trained and got better and understood better, that it would be able to more effectively use the conservation constraints and ensure that those were primarily important. So you can see here the initial results of this. So this first line is with the fixed penalty, and the second is with the stochastic augmented Lagrangian. And so you can see the histogram of the data as it was, and then the improvement. You can see this left shift in the augmented Lagrangian for the change in the density, momentum, energy, and even this L2 loss. Okay, great. So we said, let's apply it to XGC. We use TorchScript, which is inside the PyTorch API. XGC is a fairly large code. It's a mixed Fortran and C++ code. So we leveraged the C++ abilities of PyTorch, and using TorchScript could easily go from a Python-trained PyTorch model into a model that could be called inside of C++ for inference. And it was fairly minimal code. It was about 30 lines or so. So then we ran some simple tests with a simple geometry, circular. These are simpler simulations that could be run on smaller GPU clusters here at PPPL in Princeton. And the results were impressive. So comparing the CPU-only version of the collisions, the entire simulation was about 54 times faster using the machine learning collision operator. And then with a more optimized traditional solver using GPUs, even the machine learning version was still about 4.5 to 5 times faster. Okay, great. So this was useful. However, what we saw was after some time, when the machine learning collision operator was applied, we'd see this avalanching increase in density eventually. And adjusting for various things, delaying until the turbulence was established, couldn't quite account for this density rise. Okay, so we said, well, let's go back to the basics of this simple temperature relaxation test that I mentioned at the beginning. And what you can see here in the Python code, where you just take a simple input analytical function and see how this bi-Maxwellian relaxes in temperature, this is how it should look on the left. And then this is what you get on the right with a machine learning collision operator. You can see it starts to have somewhat of the right idea, but then quickly becomes unstable. And you can notice the difference in these Y scales also. Okay, so what went wrong? So our first inclination was our training didn't quite match the test. So our machine learning collision operator, because of this separable hybrid Lagrangian piece where the particles move and then the collision operator is applied, the machine learning collision operator was really predicting a single time step. Whereas really our test that I just showed you was actually applying this over and over and over again. But we felt like this actually had some bearing on how the XGC simulation itself might be acting also. But the point is that this machine learning collision operator doesn't learn the long-term behavior of the Fokker-Planck operator. And that is that you should have this temperature equilibration over long times. So although this single step learning is what was needed in XGC, we really needed to give the neural network more information so that it could have better long-term behavior. And we found overall that there was some interesting noise patterns that seemed to be imprinted when the machine learning collision operator was run over and over again over long time scales. So it may be that the neural network in this particular configuration was also picking up and learning on the noise, and that was enhanced over longer time scales. All right, so we kind of went back to some basics and said, well, how could we improve this? So if we wanted to do long-term behavior of the collision operator and ensure that that was correct, we looked at what was what's called the Maxwellian distribution, which should, for isotropic Maxwellian distribution, the collision operator should be 0 effectively. So we came up with a new normalization which better represented what the long-term behavior should be. So we normalized the distribution function divided by some effective Maxwellian of the distribution function with the same density and temperatures. And what this means is on long-term behavior, your target that the machine learning neural network is learning should be effectively flat. So we then said asked the question, can we do a sanity check to show that the neural network can learn to be in equilibrium for long times? If you start with a Maxwellian distribution function, applying the collision operator onto it should give you 0 for your change in the distribution function. So effectively what this means is your Maxwellian input to the model should result in a Maxwellian output of the model. So it's basically learning the identity transform. And so with this effective Maxwellian normalization, these Maxwellian probability distribution functions would become flat. And then this density and temperature information should be included in the absolute value of that flat distribution function. So one of the first things I noticed in doing some simple tests with UNets was, and resegs, was there's often some artifacts that are produced in the edge. And this is caused by the same padding in convolutions and is pretty well known, but we didn't appreciate how much of an effect this could have. And it was especially important when we started going to these different normalizations, as these edge effects would pop up and become important. So a simple way to avoid this uses a little more computation, but that is to pad your input distribution function to the next size up, so 48 by 48, and then on the output you effectively crop out the middle, so that you're only taking the areas that are not affected by these artifacts that come from the convolutions. And then we did some work looking at RK4 nets to generalize the solution for multiple time steps. So Runge-Kutta methods are often used in ODE solvers, and there's some recent work reintroducing this RK4 net using a single neural network weights for each step. And so here's kind of the algorithm that you have. You have this neural network represented by F, and you have the different RK4 steps, and then finally it kind of effectively averages. And this is in the RK4 method. So we did some tests with this, and the overall effect of this was that there was some important changes. So first of all, the normalization itself made a huge effect. So in doing that normalization, the median change, which you can see actually in this green, stayed much more stable over longer times. However, you still did eventually blow up. And for an equilibrium case, you should be able to do better. And so the RK4 and the padding / cropping eventually would give you a fairly good small change in the density. So we went back to the XGC simulations, and we did kind of a simpler geometry. So this is kind of a cross section of what the turbulence looks like for this particular case. And we focused on the ions since they're inherently less noisy in XG simulations compared to electrons. Okay, and we changed around the normalization a little bit. Instead of this modified divided by the effective Maxwellian, we simply applied a log transform, which gives you kind of the same transform effectively of flattening out the distribution function in space, in velocity space. So what you get is on the left, applying this, you get some stability over 40 time steps, and this is in the simulation itself, but eventually the density does increase exponentially, and so there's an instability that occurs. But this was without padding at all. When we went and we padded, you can see the nice result that we have here. Over the time of the simulation that the machine learning collision operators applied, you get this nice flat profile where the density is still not at the traditional solver levels, but is stable and not going out of control. And so interesting, like when we looked at the padding again, you can actually see most of the points are fine, but every now and then there's a configuration space point that would have a very large peak in the higher energy regions. And what this had the effect of doing is kind of propagating that error to its neighboring configuration space points, because they're all connected through these particles essentially. And so that's what kind of leads to this rise and unstable behavior. Okay, so this was a nice result. This will allow us to have a stable collision operator. We're going even further though, looking at ways to really ensure numerical precision of the density change, for example. So finite volume methods conserve particles by construction. This is how XGC actually does the traditional collision solver. So if you change by predicting the fluxes instead of predicting the delta F directly, this will give like a hard constraint on what your density change should be. So this is future work with a PhD student here, Nick McGreevy, who's been working on a global stabilization technique, which hard constrains and guarantees stability of machine learning solvers over a long time. And I think this is a really important piece of work generally in the field that needs to be looked at and appreciated, because a lot of work has been put into traditional solvers and ensuring long-term stability that I think needs to come into a lot of the numerical solvers that machine learning is trying to replace. Okay, time check. Good. All right. All right, so that was the machine learning for accelerating simulation. I want to now turn to this piece of using machine learning for simulation and experimental data comparison. So the motivation behind this work was often XGC is a large code which is more first principles based. Often we have reduced models that we use in fusion energy physics and design, and that's those are useful because they can be run more often, but often they need ad hoc simulation inputs because they don't capture all of the high fidelity physics that we know are there. So one example of this is a boundary code called SOLPS, which uses anomalous transport coefficients to basically replicate the effect of turbulence versus actually simulating the turbulence itself. And so usually what happens is a modeler will come in and use one of these codes and by hand tune these ad hoc inputs to match the simulation with experiment. But it begs the question of how do we know their uniqueness or range of validity for these ad hoc inputs? And so one of the reasons I started thinking about this is there was some work showing that you had to actually tune these parameters in a more sophisticated way than was traditionally done in order to match certain experiments exactly. And so at some level, tuning too much can give you whatever answer you want. And we wanted a way to be able to effectively look at how what the effect of the tuning would be and what the range of validity of these ad hoc inputs would be. And part of this is also motivated by experiment has a lot of information that's generated from these different from these different diagnostics, but we often don't have the time and the manpower, woman power to be able to simulate all of the different experiments that are run in these tokamak devices. But you can create fast surrogates in order to do this, in order to do the statistical inference of extracting physics parameters from your experimental data. So, excuse me. So here's kind of the picture of this that's often used of physics parameters, theta, where this represents the anomalous transport coefficients we spoke of. And you have some forward model that maps these physics parameters onto your observables, in this case, the densities and temperatures that diagnostics would measure. And what you want to do is you want to go backwards. You want to take experimental data and say, what are the physics parameters that would that underlies these observables, and do that in a way such that you have uncertainties on these parameters so you can better understand how uncertain the models are, or how uncertain those parameters are with the diagnostic uncertainties you have. So often traditional methods are used in fusion energy, such as MCMC, to do statistical inference. But these are sequential, and although there's been some interesting work in trying to parallelize and speed these up, they can often require hours, and they don't really scale to the number of experimental points in fusion experiments. So that second question I asked was, how can we utilize simulators without explicit likelihoods and ensure fast inference? So there's been some recent resurgence of work in what's called simulation-based inference, or likelihood-free inference, and using neural networks to better enable this Bayesian inference. So this is kind of the simple setup you can see in this nice paper here. You have some model or simulator and some prior over the parameters that you're interested in. Maybe not all of the parameters, but the parameters that you're interested in that go into the simulator. And you have some experimental data. So you'll sample from the prior, and you'll run many different examples of the simulator and generate this simulated data. And then you have a neural network, which takes these theta x pairs representing the input parameters and the forward model generating the observables, and it effectively learns to do the inference process so that you end up with a posterior, which if you sampled from this region, which has high probability, you see a consistent sample with the experimental data. And if you sampled from this particular region, which has low probability, you see an inconsistent sample with the experimental data. Okay, so so this is important because it can show multimodal behavior and can also, basically help us take experimental data and understand what the physics, underlying physics models would predict the parameters should be for these. So these simulation-based inference workflows using neural density estimators are used in various ways, sometimes in sequential ways where you have some target experimental data you already know, and it can kind of guide the simulation so that it covers relevant regions instead of simulating too many different areas, and help reduce the simulation cost because you're not running as many. Or you can have what they call amortized models where you're just running with a prior and sampling a lot and running a lot of simulations. But then you have this neural network model, which you can pass in any experimental data and get out the posterior. Okay, I'm not going to cover these too much, but suffice it to say, these simulation-based inference workflows have been greatly aided by what are called normalizing flows. These are bijective invertible transformations. So you set up your neural network in a very particular implicit bias, essentially, and it allows you to go from a simple distribution function to a more complicated distribution function. And effectively, what this does is when you run the inference, you're able to sample from a Gaussian, typically Gaussian distribution function, and it will give you the transformation that would be needed to get your final posterior. I'm going to skip this part. This talks a little more about neural posterior estimation and sequential neural posterior estimation. The sequential part, again, is when you have some target experimental data that you want to generate a posterior for, and neural posterior estimation is again the amortized method. So I could talk about some of the pros and cons of this, but the amortized, of course, is really nice because you can run it on many different experimental observations, but it requires many more simulations typically to cover the input space. Okay, so we did a simple toy problem proof of principle for this, where we took a simulator that was based on a fluid model for scrape-off layer transport called U-edge, and had some prior over the anomalous transport coefficients representing mainly turbulence transport. And then we generated a toy problem, quote unquote, experimental data, which was really taking our forward model with some ground truth input parameters of these transport coefficients and generating that observable. And so this was a test to see closed loop, what would the posterior look like? And could we get consistent results? I won't go into too many details, but suffice it to say, this was a smaller grid that was used, and it runs in somewhat like 10 seconds on the smallest grids. What we ended up with was somewhere in the minute time range. But these are relatively fast simulators. Right, and so we did some tests to compare against the sequential neural posterior estimation and the neural posterior estimation to say how many simulations would it take for the SNPE to make up for the NPE. And here's some results using this target toy experimental profile. This is sorry, these aren't the results. These are the toy problem that we created. So these were the theta naught parameters. This was the generated quote unquote observables that were fake or synthetic. And what we wanted to do was to see, would SBI give us back these theta knots, and how uncertain would they be? So there's a nice Python package called SBI that's been put together. Very simple, very intuitive interface, but has a lot of capability under the hood, and has a very nice format. So you can take basically any simulator that you have and be able to call that out from Python, and then be able to run these SBI workflows for your own simulator. So here was the results for the NPE. You can actually see that this orange is the actual theta knot that we were trying to see, would it replicate that? And this blue represents what the posterior sampling the posterior for uncertainties shows. And so you can see that actually, like, it gets it dead on for most of the profile. This is a radial profile in the fusion device. And the only thing, though, is at this edge region here. So you can see that the uncertainties kind of blow up here. And what this shows basically is that there's some non-uniqueness in the transport coefficients in these regions. And this is somewhat of an intuitive physics result at some level, but important to show that your simulation may be under constrained in this region, depending on what transport coefficients that you actually put. And this has an effect downstream also. And these are pair plots. So this shows the uncertainties with respect to each of the other regions. And you can see, well, you can't really see, but there's basically a red dot where it's right on target, except for these regions, again, that are in the high uncertainty range. And you can see that there's a very wide distribution for those regions. All right, so future work. So this toy example had no knowledge of noise inherent to experimental measurements. To really use this with experiment, you want to be able to include the experimental noise. And so effectively, you can do this by taking a simulation and some noise model for your experiment, and sampling from that noise model and adding it to the different pairs of theta and xi, which are generated. And so you have one theta for multiple x's effectively, and you train your neural network or your simulation-based inference workflow in order to incorporate that noise. So we're actually applying this right now to a real fusion diagnostic where we have called Llama on the D3D tokamak at General Atomics in San Diego. And this is a diagnostic which measures what's called neutral density in the edge. And so this will be able to take in the measured signal and quickly extract the neutral density, which is kind of a proof of principle of this. There are methods to do that already, but this will allow for very quick with uncertainties, and be able to be extensible to include further diagnostics to constrain what the simulation model would expect. And then further future work, creating these amortized models with a large scale number of simulations could lead to some very generic models which can be routinely applied to experimental output. And I think it's a good capacity use of larger scale HPC to run many of these simulators, even going to more detailed, higher fidelity simulations in order to be able to really understand how well do our models match the experimental data that we're measuring. And in doing so, being able to compare to more experimental data allows you to have a better feel for how good your simulator is and where are the regions that it's breaking down and that you need further work to improve. And then just a small future work. There's been many people have seen Stable Diffusion and DALL-E 2, these nice neural network models which allow you to specify a prompt, such as a photograph of an astronaut riding a horse, and it generates the image for you. These are typically based on score-based models and have been very popularized by, again, DALL-E 2 and Stable Diffusion. these were also applied to the same simulation-based inference workflow. And what's really nice about that you can see from this nice work from DeepMind is they have this true posterior, which is bimodal. And if they're using the typical normalizing flows, you can get some spreading between these two modalities in regions where there shouldn't be any probability density. But when you use the score-based model, because these are because they're based on these diffusion processes, they are much better able to separate out these two different modalities. So I think this is a promising area to further explore. Okay, so with that, let me conclude. So I think machine learning shows a lot of promise for accelerating simulation and enabling stronger connections between simulation and fusion energy experiments. So I showed you this encoder-decoder style neural network, and that it was trained to replicate this nonlinear Fokker-Planck collision operator. We sped up the simulations by 5x, but at the same time, we had to be careful that the neural network was not only matching the conservation constraints, but matching the long time behavior. And custom data normalization and training constraints played a key role in that. And then I showed these simulation-based inference workflows using neural networks and normalizing flows that allows for fast inference of physics quantities from experiment. So this is nice because it gives you uncertainties on ad hoc parameters and simulations, helps see where your simulator physics models break down, and reduces potentially the number of simulation runs needed for a result. And with that, I thank you for attention and happy to take questions.
Thank you very much. So yes, please, if you have any questions, write them in the neural network chat function. So have you tried other neural network architectures, and what are the trade-offs of each?
Yeah, so for the collision operator stuff, we've tried various operators, and we're still in the process of trying out new ones. So I think there's a lot of promise with many of the neural operator architectures that are coming out. So the Fourier neural operator coming out of Caltech and NVIDIA. We've been working with them to apply that. So, and beyond that, we've tried even simple UNets. There's some nice work out of Microsoft that's going back and forth about FNOs and UNets and different flavors of those and how they perform. I think these are really healthy things for the field, and they've created some benchmarks also to help kind of coalesce and clarify when certain models will work well and when they won't. So yeah, right now I think the data normalization was an extremely important part to get it to train well, and then after that, using the Fourier neural operators or other architectures is something that we're looking into.
Great, thank you. We have another question. Yeah, so have you tried testing so previous work on use of machine learning for plasma physics showed difficulties when extending the work done on one fusion device to another fusion device. So the question is, have you tried testing these models with other magnetic confinement fusion machine?
Yeah, so let's see. The XGC simulation stuff is pure simulation, and that should work in and of itself. The simulation-based inference stuff, that was really a toy model, which was just a single machine. So we haven't tried it on new machines, but that is one of the benefits of using these simulation-based inference workflows, because if your simulator should be working on one machine and working on another machine, you should be able to adapt that pretty easily. And there's some nice work from a group led by Bill Tang here out of PPPL, looking at creating surrogate models for some of these fast simulators and looking at different machines and how to better make sure that the models that are created are cross-compatible. So I think data-driven, it becomes a very, you have to take a lot of caution and you have to be careful in how you do comparisons. But adding in the simulation-based piece potentially gives you an easier avenue, especially in things like ITER, where there are certain things that we need to make sure we know from day one in ITER, and being able to leverage simulation to help us know that beyond just data-driven techniques is extremely valuable.
Great, thank you. Someone asked what causes the convolutional model to create artifacts near the image edges. Is it because the training data is too uniform near those edges?
No, it's not because of that. It's actually it's kind of an interplay with how the convolution works when you have what's called same padding. So I mean, you could look at this at any, like even a simple convolution test where you effectively overrun the bounds at some level. And what do you do with that afterwards? And so that introduces, especially with these deep neural networks where you have many layers of convolutions, that introduces the potential of these artifacts. Now it may be worse because of the inherent noise that is in these distribution functions, because it's from a particle and cell code. But you actually see this across many, not just like simulations like this. You see this in normal natural images also, and things like that. So it's a pretty well known. It's pretty well known when you look at it, but at the time I wasn't looking at it. So in hindsight, you can see it in various places. So
Okay. And how long did you run the simulation for? And do you think it can be run faster using different machine learning models or other parallelization methods?
Yeah, so that particular simulation, so those kinds of simulations you'll run for thousands of time steps. That particular case that I showed you was a couple hundred time steps, just to show. And so I am running it out longer to see how stable it is over the thousands of time steps. Though my guess is eventually it will also have some instability that'll occur. Even it's longer than what we had previously, but eventually, without some of those hard constraints, my expectation is it won't be the final solution. Sorry, what was the second part of that question?
If do you think it can be run faster using different machine learning models or other parallelization methods?
Yeah, that's a good question. So actually, RNNs are kind of slow. So I would expect that if we can do some of the FNOs even, or even some of these simpler unit architectures, if we're careful, I believe that can speed up things. So some of that we're going to explore, but you have to be also a little bit careful. The collision operator or routine is not 100% of the XGC code either. There's a lot of the particle pushing and things like that is a big piece of it, typically dominant sometimes. And so premature optimization is the root of all evil, I guess. So yeah.
Great, thank you. What are your thoughts on DeepMind's work with fission plasma control?
Yeah, right. So I'm glad somebody brought this up, because it was a really excellent work. I'm not a control expert. The problem that they tackled was a good proof of principle, I think. And if you look at what they did, they had, I mean, maybe we can call it loosely a simulator, but it was basically based on a simulator so that they could control the boundary of the plasma or the shape of the plasma. And so that was a really nice result, because they showed that they could control it extremely well using this reinforcement learning technique. Extending this is probably the key difficulty. One of the difficulties in simulating plasma tokamaks generally is there's a real simulation to real gap, where we don't know all of the physics, or at least the simulators that we have that can run in an open amount of time, or a small enough amount of time, don't always recover all of the physics. And so when you're looking at reinforcement learning and adding in more physics detail, there's going to be a real reckoning, I guess, with the simulation to real gap. But other DeepMind work, I think, has shown a lot of promise in reinforcement learning for like continuous space. So some of the like video game type of work, StarCraft or Dota, those have shown a lot of promise with like continuous spaces and hidden hidden states. And so I think that's a lot of what you would need in Fusion also. But yeah, the sim to real gap is really the key piece that I think needs to be faced up. And that's kind of a broad general subject. But how to learn when you're unsure, when your model is not completely trustworthy is something that needs to be tackled.
Thank you. For a simulation-based inference, how can you effectively work with larger, more expensive simulations, which have many more input parameters, such as the mesh?
Yeah, this is something that I've thought about, and I don't have the absolute answer. But I actually think you start to see some hints even from the stable diffusion side. So if people have seen things like ControlNet, actually, you are able to condition on a somewhat complicated structure and use that effectively to generate these images. And I think you can start to do some similar things, but the key is being able to generate some latent space representation of things like a mesh, for example, or some input parameters that you're interested in. So when your input parameter space kind of blows up exponentially, you'll probably have to go to a latent space in order to do that effectively. And I think there's some real possibilities there. I'd like to explore them. Or have somebody explore them. But I think that's how you would have to do it, because you can't scale this up unless you use a lot of compute for each individual parameter on like a large mesh, for example.
Great. Thank you. Where do you see machine learning for numerical solvers going in the future?
Yeah, this is a good question. So I listen a lot to various people who have opinions on this, and I think there's been actually Nick McGreevy, the student I mentioned, has also done some work at looking at a broad range of fields where machine learning has been applied for numerical solvers, and has shown some really good work on areas where like benchmarking should be improved or comparisons need to be improved. I think these are areas that, as there are more standard benchmarks similar to kind of the ImageNet days of computer vision, I think that can help clarify especially what the issues are. And so I really applaud this work out of Microsoft. I don't remember the first author's name, but creating a benchmark for using machine learning for solving various PDE equations. I think there needs to be a lot in terms of just coalescing around what really works and how well it works. And then after that, there's been a lot of research and work put into traditional solvers in terms of robustness and conservation quantities. And I think that there needs to be a more, we probably need to do better at tying in with the traditional numerical solver community and looking at some of those issues and addressing them completely.
Okay, great. Well, thank you everyone for joining us. Thank you, Dr. Michael Churchill, for this interesting talk. And yeah, see you next time.
All right, thanks all.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the eShop, and build your personalized AI for Good program. Let's shape the future of AI for Good.
AI is a powerful tool.
This summit can help ensure that artificial intelligence charts a course that benefits humanity and bolsters our shared values.